Okay, 8.3 composite functions. Quick review of what we've already done. I'm going to jot down a couple of sentences. Feel free to do that also on your big blank page of notes. We're not going to fill up that page entirely, but we have learned 4 ways of combining functions. We've learned 4 ways of combining functions. They are the basic operations: addition, as in the sum; subtraction, that's finding the difference; multiplication, which is finding the product of 2 functions; and division, which is quotients, where one function is the quotient of 2 other functions. There is another type. It's called, there's another type when occurs when one function depends on another. So another type of combined function, and actually let's not even bother writing that. I'll just give you the definition of what we're working with. So today we're working with composite functions. And a composite function isn't built by addition or subtraction or multiplication or division of 2 different functions, but it is a function that depends on another function. And that'll make more sense as we move along. So it's a function that depends on another function. It's formed when one function is substituted into another function. And you can even say, this is probably helpful, in the place of the variable. In the place of the variable. Okay, so we're looking at composite functions today. It's a function that depends on another function. And what does that mean? Well, if you take a function and you put it inside another function where the variable is, then you have a composite function. Okay? So again, we'll break that down in a couple different ways. We'll give you some notation for it, and then a bunch of examples to think about. So under this composite function business, you can take this note. It looks like this: f of, and then instead of writing f of x, instead of having x, just the variable here, we're actually going to put in a whole nother function. Okay, so in the place of the variable x, we're inserting another function g into the function. Okay, so here, g depends on x, and f depends on g of x. So f depends on the function g, which depends on x, and that's our composite function. So what does that mean? F of g of x is read just like that. F of g of x. It's formed by subbing g of x into f of x for x. The order of these functions is very important. F of g of x is different from g of f of x. Okay, it matters which function goes in for the variable. Okay? Another way that you might see this noted, alternate notation, is fog x. So that looks like this. It's an f for the function of f, and then a little circle, and then a g, and then in brackets x. So this means the same, f of g of x. So you would sub x into g, and then you would sub g of x into f of x, is one way to solve these things. So you should still have about half a page. Before we get into example 1, I'm going to give kind of a little pre-example, okay? In example 1, you have this. You have let f of x equal x squared, okay? Now, if y equals f of x, that's easy. We know y then equals x squared. That's just one function f that depends on x. And if we needed to find the value of the function when x is 2, if we needed to find f of 2, we would simply sub the value 2 in for x. We'd end up with 2 squared, which equals 4. Okay, that's pretty easy. That's just finding the value of the function when x is 2. When we're dealing with composite functions, we're finding the value of the function when x is another function. A function inside a function. So when we write, and maybe I don't need to write it, maybe I will. If y equals f of, and then in brackets, g of x, rather than substituting in a value for x, we're subbing in a whole nother function. So the value of g of x depends on x. The value of the function f depends on the function g of x. So far making sense, kind of, a little bit? Okay, we're going to carry on to example 1. All right, I believe in your booklet the pieces of example 1 are named incorrectly. Example 1, what we're given is f of x equals x squared, and g of x equals x plus 3. Those are going to be the functions that we work with, and we're going to make them, we're going to combine them in different ways, different compositions, different ways to bring them together. In A, we are asked to determine the composite function y equals f of g of x. Okay? So all we need to do then is look at what f of x is. So I'm going to first look at f of x. F of x is x squared. Now what happens if I, instead of subbing a value in for x, instead I write this, f of g of x. What I've done is I've subbed in g of x in place of x. And what does it do on this side? We're not gonna have to write it funny like this every time, but I'm gonna actually just write, yeah, g of x squared. That's what happens. We're taking the function of g of x and squaring it. Okay? Well, now I know what g of x is. It's x plus 3. So instead of writing g of x inside my bracket that gets squared, I know that x plus 3 has to get squared. Okay, that's what it means to take g of x and do f of x to it. F of x says square the variable. G of x says add 3 to the variable. So I'm going to add 3 to it, and then I'm going to square it. Okay? This is basic algebra. This is a binomial squared. We know that this ends up as x squared plus 6x plus 9. Okay, that one is done. It's a quadratic function. There are no restrictions on x. So the domain is all of the real numbers. we could graph it, and basically we'd find that this is a parabola that has been translated to the left 3 units. Still has its vertex on the x-axis. So you do have some space to sketch it there. And the easiest way to sketch it is to look at it in this format. This tells us that it is a parabola with a horizontal translation 3 units to the left. So I go 1, 2, 3. This tells us its y-intercept. So let's say 5, 10, we're at 9. This isn't exactly, my scales are different on my x and y axis, so it's going to look fatter than it maybe should or could. At any rate, looks something like that. It's already labeled.
Wait, there's plus 9. Why is this so far low? Oh, no, never mind.
Y-intercept. Yeah.
I see. Oh, you're awesome.
Okay, that's the easiest way to combine functions. And just to show that putting g of x inside of f of x is different from putting f of x inside of g of x, our next one in B says take g of f of x. So how are we going to do that? Well, I'm going to start by taking g of x, okay? So I'm going to look at what g of x is. G of x is x plus 3. And now, instead of putting a value in wherever I see x, I'm going to put in the function f of x. So now we have g of f of x, which is basically I'm putting x squared in anywhere I see an x in g of x. So I end up with x squared plus 3. Don't get tricked. It's not the same as the one we just did. Okay? This is already simplified for us, really. It is, again, quadratic with the same shape as x squared over here, but instead of being moved to the left 3, what's happening to it? How would you graph this quadratic?
It's just x squared in the middle plus 3.
Yeah, it's just been moved up 3.
Vertex is at 0, 3.
All right. So that's to show that they're different. Is it always going to end up that one moves it to the left and one moves it up? No. It's just because we ended up with a quadratic and they're pretty simple, basic functions that we're starting with. But it's to show that it's different. It matters which one you put inside the other one.
What about E and F?
Okay, example C, 1C. Okay, we're working with our same 2 basic functions. C asks us to take the composite function f of x. Okay, so now we're putting f of x inside f of x and figure out what happens there. So again, I'm going to start with the function that's on the outside. I'm just going to write f of x and copy it down. F of x is x squared. Now, if I'm going to take that variable, and everywhere I see an x, I'm going to put in the function f of x, that means I'm going to be putting in x squared everywhere I see an x. So one other way to do this really easily to make sure you don't mess it up is to do brackets and make sure you have that squared outside. That's what's happening to the variable. And now you can think, okay, what am I putting there in place of x? I'm putting x squared in its place. Power law of exponents tells me that this is x to the power of 4. So this is a quartic power function being the simplest polynomial, just has one term, and it's quartic. If we remember way back to the beginning when we drew some of these, or identified them at least, it's a parabola. It's still called a parabola, but it's actually more of a U at the bottom, and it turns up way faster. So below zero, between 0 and 1, it stays lower because a decimal multiplied by a decimal more and more times, it actually gets smaller. And then once it passes 1, it grows really, really quickly. So it's kind of a flat U shape, and then it trends up really quick. And its vertex is still 0, 0. The domain of this function, no restrictions on the domain. The range, y must be greater than 0. All right. D. How are we asked to combine D? We're going with y equals g of x. So we have a composite function where g of x is getting substituted into g of x. So the first thing we're going to do is take down g of x. Tell you what, I'll pause here and you guys try to do this one. And you can check the board to see how you did. So g of x just ended up being a linear function. Slope of 1, y-intercept of 6. Something like that. 6 there, negative 6 here. And no restrictions on the domain or the range. And the last one is E.
We actually have 2 more.
Yeah, that's just because the notebook is a copy and paste. It's easier to make 6 than to make 5.
Okay.
So you have E, and this one we get into an inverse function. And I'm going to ask you what you think is going to happen here before we actually do it. But we're taking the inverse g of x, but we're going to take the inverse of g of x. So the inverse g of x. What do you think is going to happen here? What happens if you take the sign of something and then you inverse sign it?
Well, it's probably going to equal 1. Wait, no. Yeah, so it's going to be a constant equal to 1 because you're multiplying it by its reciprocal, which is always going to be 1.
Okay. What if you take the number 4 and you multiply it by 3 and then you do the inverse operation of multiplication by 3? So you multiply it by 3 and then you divide it by 3. What do you end up with?
Okay, so it's going to be equals y equals x.
So whatever you started out with, you're doing something to it and then undoing it. It's basically what inverse means, right? So here we go. Let's find that out. We've got the first thing that we need to do is to determine what an inverse function for g of x actually looks like. What is the inverse g of x? So first, comma, determine a function for, or the function, the inverse of g of x. How do we do that? Do you remember how to do that? What you end up doing is if g of x is x plus 3, then you substitute y for g of x. So you end up with y equals x plus 3. So far, nothing too tricky. Then what you do is you actually interchange the x and the y. Is that familiar to you at all? Remember doing that? Okay, so I'm going to write that down so that we remember it. Interchange x and y. This will work with any type of function. So now it looks like x equals y plus 3. The next step then is to solve for y, or isolate y again. And if you can do that, you'll have the inverse function of the one that you started with. So in order to get y by itself, we're just going to subtract 3 from both sides. So we end up with y equals x minus 3. Therefore, the inverse function g of x is x minus 3. Now in this one, it's really easy to see. If an inverse function undoes something, and g of x, you're adding 3 to the variable, then to undo that, you're subtracting 3 from the variable, from what you have. Okay? So now let's go and actually solve this one. We're looking for the inverse function, g of x, which we just determined as x minus 3. But now we're not subbing in a value for x. Wherever we see x, we're going to sub in the function g of x, which is x plus 3. So for this x, I'm going to have a bracket. That's going to be my x. And then in there, I'm going to sub in x plus 3. Now it's really easy to see this is just x plus 3, x minus 3. Okay, you'll have to do this with more difficult functions along the way. But x plus 3 minus 3 is just x. No matter what, when you get this, you're just going to end up with x. You're going to end up with what you started with. Okay? And graphing x, it's just a linear equation. It's a diagonal line through 0, 0, passes through 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. Okay, this is y equals x. Domain and range, no restrictions. Okay, in example 2, we get some more difficult functions to work with, and then we're actually going to be evaluating them when we're given an exact value for x. So we have let u of x equal x squared plus 3x plus 2, and w of x equal 1 over x minus 1. And in A, we're going to evaluate u of w of 2. There are 2 ways to do this. What are the 2 ways?
I only know one way.
Good. We're going to do this with 2 methods, both ways, and then talk about which one we like better. We're just going to do it 2 ways for A. We won't do it 2 ways for both. But we have method 1, which is determine u of w of x, then sub x equals 2. Method 2, determine w of 2, then sub into u of x. So method 1 first. We're going to determine the composite function and then sub in to wherever we see x. So again, following the same steps, we have u of x. You might be at a point where you don't need to write down u of x in order to do what you need to do, but I'm still going to write it down every step. And everywhere I see an x, I'm going to sub in w of x. So u of w of x would look more like this. I'm going to make sure I have my brackets, and I'm going to make sure that this thing gets squared. But I'm going to plug in w of x, which is 1 over x minus 1, close bracket, squared, because that's what's happening to it in u of x. And then I have 3 times x, And everywhere I see an x, I'm subbing in w of x, which is 1 over x minus 1, and my constant plus 2. I've done this. I don't really need to go through the work of simplifying it further than this. From here, I can sub in the value of 2 everywhere I see an x. Okay, so we've got u of w of 2 then is equal to this. Just copying down exactly what you have, but everywhere you see an x, you're going to sub in 2.
Conveniently with 2, every every time you do go to a wx, you get 1.
So nice of them, hey? All our denominators work out nicely and squares. So in the denominator here, 2 minus 1 is 1. 1 over 1 is 1. 1 squared is 1. Same thing here, 2 minus 1 is 1. 1 over 1 is 1. Times 3 is 3. And we add 2 at the end. We end up with 6. So the value of this composite function when x is 2 is 6. Okay, and that one we determined the composite function first and then we subbed in. On the other side, we are determining the value of the function w at x equals 2, then subbing it into our quadratic there. So here we go. W of x is 1 over x minus 1. Sub in 2. W of 2 is 1 over 2 minus 1, which equals 1. Again, you can see how this would be more difficult with a harder function or with a number that isn't 2. Now what? We take our value for w of 2 and we sub it into u of x. So here we go. U of x is x squared plus 3x plus 2. That means u of w of 2, where I already know that the value of the function w at 2 is 1. And then I just subbing in 1 everywhere I see an x. And working it out, and we get 6. So you can decide which method you like better, which one is easier for you or which one is faster for you. And again, you don't need to necessarily copy out every step like I have been doing each time. But if you're going to skip a step, make sure you do it right. And in B, we're going to evaluate w of u of negative 3. So the value of the function u at negative 3 can get subbed into w, or we can determine the composite function first and then sub in negative 3. We'll do it using method B, method 2. So I'm going to find the value of the function u at x equals negative 3. So u of x is already there for me. I'm just going to go u of negative 3, sub in negative 3 everywhere I see an x, and make sure I don't forget what the function tells me to do to it. So negative 3 squared plus 3 times negative 3 plus 2. Be careful about your signs and all of those things. Negative 3 squared is positive 9. 3 times negative 3 is negative 9. Plus 2, that's easy. That's going to be plus 2. And now in my next step, I'm subbing that into w of x. I'm not going to copy down w of x again. It's for me right here. But everywhere I see an x, now I know I'm going to be putting in 2. Okay? This part would cause a common error. So you're actually writing u of negative 3. So the temptation would be to put negative 3 in, but you're not going to do that. U of negative 3 is 2. The value of the function at negative 3 is 2. So now that's the value that we are putting in here. Okay? So now everywhere that I see a x in the function of w, I'm going to put a 2. 1 over 2 minus 1 equals 1 over 1 equals 1. Okay? So the composite function u of w at the value of x equals -3 is 1. In example 3, we're using composite function to determine music sales revenue. This is definitely dated, but hopefully it still makes sense. So we have a music store. It traditionally made a profit from sales of CDs and cassette tapes. Familiar with what CDs are? Yeah, we know what a CD is. And a cassette tape, we know what that is. All right. Carrying on then. The number C, measured in thousands of CDs sold yearly as a function of time in years since the store opened, can be modeled by the function C of t equals -0.03 t squared plus 0.5 t plus 3. Talking about the basic meaning of this. It's multiplied by 1,000, right? So in the year that they opened, they sold 3,000 CDs. It's a quadratic function and it opens down, okay? So we are going to graph it in A, but I'm just going to do a sketch of them for us rather than get out a graphing calculator or a Desmos or something like that. But basically, this is a function that goes like this. And eventually the sales of CDs plummets. Okay? How else does this store make money? They make money by selling cassettes. And the number T, measured again in thousands, of cassette tapes sold as a function of time can be modeled by the function. Should have color coordinated things here. T of t, capital T, being the function of cassette tapes, 1.5 minus 0.1 t. So they're starting out in the year of opening selling 1,500 cassettes. I'm just changing my colors so they actually coordinate with my functions. And every year after that, they sell 100 fewer. Okay? So they're starting here at about 1,500, right? 1,500. And they're just going down, downward trend. And after 15 years, they should hit the bottom. Okay? This isn't super great, but it goes across a little more gradually. Something like that. All right, we've graphed them. We have a decent idea what's happening. The total revenue, R, from sales of CDs and cassette tapes together is modeled by this composite function. So now we're going to be given a composite function for revenue as a function of time. And it is, big square bracket, 3 CD function plus 2 times our cassette function times 1.04 to the power of t. Develop an algebraic and graphical model for the store's revenue and then interpret it. So in order to do that, all we're going to do is sub in what we know about these functions, apply the distributive property, and then go ahead and simplify. So here we go. What do we see? We know that we are going to have 3 times the function given for CDs, which is -0.03 t squared plus 0.5 t plus 3, close bracket. We're going to add to that 2 times the cassette function, which is 1.5 minus 0.1 t. Close off that big square bracket and multiply it by 1.04 t. to the power of t, sorry. Okay, I'm just going to work quickly. Sounds like we're moving out soon. So this ends up being, distribute 3 to each piece of the trinomial here. We end up with negative 0.09 t squared plus 1.5t plus 9. And it's all, if I distribute this, I can just do so within the bracket here. 2 times 1.5 is 3. 2 times negative 0.1 is minus 0.2t. And multiplied by 1.04 to the power of t. Group like terms in order to simplify. I have 2 terms with t in it, and I have 2 constant terms. So we have in the bracket negative 0.09 t squared plus 1.3t plus 12, and the multiplier of 1.04 to the power of t on the outside. So this is a simplified revenue function based on the function c and the function t. It is a quadratic and an exponential function. Okay, it's the product of a quadratic and an exponential function. So to illustrate this, we would do this on a graph. I'm not going to do it on a graph. I'm just going to draw it on our graph. Basically what happens here is that it goes up like this and then trends down.
We're singing, I don't know if you know that.
Yeah, we're going to come real soon. And then if you were on Desmos or a graphing calculator, you could figure out where the combined maximum is. Actually, the combined maximum, my graph isn't super accurate. It should be over here somewhere. Should be over here somewhere. And then it trends down pretty hard.
So I'm probably going to do the test tomorrow then, or finish it.
Yeah, sounds good. What does this say about this business, this music sales business?
It's not.
It's not looking so good. They need to figure out another business structure here, selling other products.
It's like a good idea at first, but they're gonna have to like have a plan B.
Yeah, gonna have to have a plan B. They reach their maximum revenue in their 11th year of business, which you would have figured out on Desmos. You wouldn't do that by hand. Okay, practice problems are from page 447, numbers 1 to 16.